Hello, ladies and gentlemen. We're going to be doing the last day of Chapter 19 notes, day 4. And our focus today is going to be on titrations. Now, in order to understand titrations, we need to look at neutralization reactions. These are the Arrhenius acid-base reactions that we looked at day 1. The complete reaction of a strong acid and a strong base is called a neutralization reaction. So this is where you have your acid and base combined to form a salt and water. Now the experimental process of determining the molarity of an acid or a base through the use of an acid-base neutralization reaction is called an acid-base titration. So in a titration, the known molarity of one substance is used to find the unknown molarity of another substance. Solutions of known molarity, and I'm going to be asking you this question a couple times. So the ones that give you the molarity in the beginning of the problem, those are called standard solutions. All right, and we have two different points that occur during a titration, an equivalence point and an end point. The equivalence point is the point at which the moles of hydrogen are equal to the moles of hydroxide. Now, technically, the moles of hydrogen are equal to hydroxide when you have a neutral solution. You have a pH of 7. The only way that we can identify an equivalence point is if we have a pH meter with the titration, and that pH meter would tell us when we reach that equivalence point, the pH of 7. Most of the time, and if we were doing this lab in class, we would be finding something called the end point. The end point gives us a visual to know when the reaction is completed. It's the point at which the indicator starts to change color in a titration. So the example that I have down here is an example of using an acid in the Erlenmeyer flask and phenolphthalein as our indicator, and this is what we're going to use in the lab that I demonstrate for you. And then they're using a base being added to the Erlenmeyer flask there. In the beginning, the acid and the phenolphthalein is clear. So this is before the end point has been reached. Now, when you add enough base to it and it's very, very close to the equivalence point, it just goes slightly over. So the solution is slightly basic. We've reached the end point, and we can tell that when we get a real faint pink color. So again, it's just slightly basic. In the last image here, this is if you add too much base to it. If you add too much base, the indicator is going to turn a bright pink. So we call this an overshoot. And this has happened because too much base was added. Hopefully when I do this lab for you, I do not get that hot pink color, but we will see. Honestly, it's one of my favorite labs of the year, and I'm so sad we're not doing it because students really strive to get this light pink color. It's kind of a fun thing, a little competition for students and lab partners and such. But like I said, I will show you what the lab looks like on Friday. All right. So at neutralization, remember that the moles of hydrogen are equal to the moles of hydroxide. And we call this the equivalence point. This is when your pH is exactly 7.00. Well, how do we find moles? How would we find the moles of either hydrogen or hydroxide if we're given the other information? Couple of different ways. We're going to use stoichiometry. It's a term you haven't heard for a while. And we're going to use dimensional analysis. If I know the volume of my standard solution measured in liters, I can multiply that by the molarity of my solution, which is my standard solution, my known molarity. And remember, molarity is moles per liter. That will give me moles. then I can use those moles in a mole ratio from a balanced equation to figure out the moles of my unknown substance. So that's what we're going to be doing for these calculations here. So in order to find an unknown molarity, the first thing we want to do is write out our balanced equation. That's our neutralization reaction between an acid and base producing a salt and water. Then we're going to use stoichiometry to convert the volume, and it needs to be in liters because molarity is moles per liter. So we're going to convert the volume in liters of the known substance to the number of moles of our unknown substance needed to neutralize it. All right, so this is going to be a two-step problem. First, we're going to use molarity as a conversion factor. And then we're going to use mole ratio to find the moles of our unknown. And once we have our moles of unknown, we're going to take those number of moles and divide it by the volume in liters of our unknown substance. And that moles over liter will give us our molarity of our unknown. All right, so we're going to walk through a couple of problems here to make sure we're understanding this idea. So for the first problem, what is the molarity of a hydrochloric acid solution if it takes 68 milliliters of 1.2 molar sodium hydroxide to neutralize 25 mils of the hydrochloric acid? All right, so step one, we said that we are going to write out our balanced equation. Remember, when you have hydrogen and hydroxide, they have to equal, and those two substances are always combining to make water. I have one hydrogen, one hydroxide, so I'm going to make one water molecule there. Left over, I have a chloride ion and the sodium ion. It's a +1 -1 charge, which means we produce one of each. We're making sodium chloride. All coefficients here are 1 because we made one water and one sodium chloride, and you have one sodium, one chlorine atom in that compound. All right, the next step is starting with our standard solution. Sodium hydroxide here is our standard solution, and we know that because we know its molarity. The molarity is 1.2 molar. So it said that we're going to take our volume and multiply it by our molarity to get moles of sodium hydroxide. But our volume had to be in liters. So you got to make sure you convert milliliters into liters by dividing by 1,000. So we're starting with 0.068 liters of sodium hydroxide solution multiplied by its molarity, 1.2 moles per 1 liter. Molarity is moles per liter. And then we're going to turn it into moles of our unknown, which is the hydrochloric acid. We do that by using stoichiometry. So moles of NaOH are on top. I'm going to put those on the bottom. And moles of our unknown hydrochloric acid goes on top. Well, in our balanced equation here, I have 1 mole of HCl for every 1 mole of for every 1 mole of sodium hydroxide. So those are both 1. So then we would calculate and round with sig figs. Fewest number of sig figs here is 2. So my answer will have 2 sig figs. And that comes out to be 0.082 moles of hydrochloric acid. Now, my goal isn't to find out how many moles of HCl I have. It's the molarity of HCl. So to get molarity, we said we have to take our moles of our unknown and divide it by the moles or the liters of our unknown. Well, I have 25 milliliters of HCl. That is the volume of my unknown. So 25 divided by 1,000 gives me 0.025 liters. And that in turn comes out to be 3.3 molar hydrochloric acid. Okay, we're going to do one more problem to make sure that we're understanding this concept. What is the concentration of sodium hydroxide solution if it takes 12.4 milliliters of 0.24 molar sulfuric acid to neutralize 9.5 milliliters of sodium hydroxide? All right, so we're going to start by balancing our equation. Notice here I have 2 hydrogens, 1 hydroxide. Remember how we said they have to match. So I'm going to put a coefficient of 2 here to give me 2 hydroxides for my 2 hydrogens, which means I am producing 2 water molecules. Now I also have a sulfate, which is SO4 2 minus, and I have 2 sodium ions then, which is what I need because sodium's a +1, sulfate's a -2, gives me 2 sodiums, 1 sulfate. So my salt is Na2SO4, sodium sulfate. All right, next up, we are going to identify our standard solution. Standard solution is the solution that we know its concentration. We know the concentration of sulfuric acid. So this is our standard solution, and this is where we're going to start our problem. We take the volume of our standard solution, which is 12.4 mils. That comes out to be 0.0124 liters. And we multiply it by the molarity of our standard solution, 0.24 moles of H2SO4 per every 1 liter. Now we're in moles. Those will cancel. Let's change the color of that. So those will cancel. Now we're in moles of H2SO4, so that's going to go on the bottom here. We need to find the moles of our unknown, which is sodium hydroxide. So moles of sodium hydroxide are going to go up there. Now to convert from moles of sulfuric acid to moles of sodium hydroxide, we're going to look at coefficients. The coefficients of H2SO4 is a 1, and the coefficient of sodium hydroxide there was a 2. Now we've figured out moles of sodium hydroxide. So we calculate there 0.0124 times 0.24 times 2. Fewest number of sig figs there is 2, so that rounds to 0.0058 moles of sodium hydroxide. We need to divide it by the liters of sodium hydroxide. Well, I have 9.5 milliliters, which divided by 1,000 is 0.0095 liters. With 2 sig figs, my final answer there comes out to be 0.61 molar sodium hydroxide. All right, so to do these problems, you need to balance it. Start with the standard solution, multiply volume times molarity. Using mole ratio, turn moles of known into moles of unknown, and then divide by your liters of unknown. All right, if you have any questions on these, make sure you ask me. And this is it for Chapter 19 notes. We'll see you guys soon.